All right. Okay. So now this equation still have a few terms that involves the velocity at the wall, right? So what do we use to get rid of that? Conservation of mass and also possibly momentum, right? Both actually involves this velocity here. So the conservation of mass tells us the dx of the integration of ue minus u dy is equal to what? Well, so this is something we derived last time, right? So we looked at the mass conservation equation. The divergence of ue is equal to 0. The divergence of ui is equal to 0. The divergence of u is equal to 0. We subtract them. Then we get the difference in the mass flux of the defect is equal to, yes, it's just equal to VIW, right? Okay, so if we replace this particular VIW, and we also have to replace this VIW and this VIW. The correct thing to do is to replace that with that in the momentum equation. So what's in the momentum equation is integration of ue square minus u square dy is equal to the product of two terms. The first term is a velocity is a momentum flux from the wall, so that's a ue, and there is also another term from the pressure gradient. Right, tau over density. That's right. That's right. Yeah. Okay.
Evaluate at the wall.
Right, at the y equal to 0. All right. Okay. So next we are going to combine these terms. So first let's get rid of this term. So what do we have to do here? So we want to ultimately derive an equation that we can relate to the kinetic energy thickness, which is ue to the cube times 1 minus u square over ue square times u dy. So this, if you pull this ue cube out of this equation, you get the kinetic energy thickness, which is defined as theta star, defined as integration from 0 to infinity, 1 minus u over ue. Also, this is ue times u over ue dy. So this is what we are trying to derive, and if you write this out, this is ue to the cube. Yeah, it's a square, right? So if you multiply that out, it's actually not ue cube, because one of the ue actually cancels here. You have ue square times u minus u to the cube, right? So this is the equation we are trying to derive, and what we have already is the dx of ue to the cube minus u to the cube. So what's the difference between this and this is actually, let's write this out, is actually equal to ue to the cube minus u to the cube plus, actually let me write minus ue to the cube times ue square times u, right? So this term is the difference between what we want to derive and what we have over there. Okay, so this is equal to first term we want to keep as it is because we want to use this equation we just derived. And the second term is ddx of ue square times this, times the mass defect, times integration of ue minus u dy. So we need to plug in the equation for the mass defect into this equation. Okay, so what we can derive, I think let's just write out the final equation, which I have over here. So if you integrate over, if you take the derivative, okay, of the integral from 0 to infinity, half of ue to the cube times 1 minus u square over ue square times u over ue dy. So that is basically ue to the cube times half of ue to the cube times the kinetic energy thickness. What you get is everything cancels out except for the dissipation, where the dissipation is defined as integration from 0 to infinity tau xy du dy divided by the density. Alright, so it turns out when you plug in this equation up to here, the pressure term cancels with all these right hand sides, and what you have is only the change in the kinetic energy defect and the dissipation. And from this equation you can derive the x derivative in the momentum thickness, in the energy thickness, because you can write this as the x derivative of half of ue cube times theta star, which theta star is the integration of everything except for this half of ue cube. If that is equal to d, that means you can factorize things out.